Good morning, good afternoon, and good evening, everyone, depending on where you are. Thank you very much for joining us this evening for the first ever iPHA community meetup. My name, for those of you who've been on for the last half an hour, you already know, is Georgia. And together with my colleague Carl, we run the International Passive House Association. We're really glad that you could all join us tonight, and we hope to make this series of iPHA community meetups a place for people like-minded passive house individuals to meet from all over the world and maybe learn something new while they're at it. For those of you who are looking to renew your passive house designer or consultant certification, you'll receive 1 point towards renewal for each iPHA community meetup that you take part in. We'll be exporting the list of participants tonight exactly for that purpose. So if you are looking to renew, this is an option, and there'll be a series of these events where you can collect points during this time period when you're most likely spending a bit more time at home. The good news before we even begin tonight is that our next iPHA community meetup is actually already set for the 20th of April. It'll take place at 6 p.m. Central European Standard Time, and it'll be a presentation from New York Passive House's Andreas Benzing. Tonight, though, we have Passive House Institute's Wolfgang Hasper with us. He'll start this series off with a talk on commissioning of building services or building service systems. And we will ask you to hold your questions until after the presentation, at least the questions via your microphone. There'll be plenty of time for discussion after the presentation, but do feel free to write your questions in the chat box. We will collect them for the discussion part later this evening. Apart from that, if you do have any problems at any point with the sound or you can't see the screen, please do also use the chat box. Carl and myself will be looking out for those things, and we'll solve the problem as quickly as we can. So with that, it's almost 5 past, so I'll hand over to Wolfgang. A big thank you to him from us for hosting this first presentation, and we hope you enjoy it as much as, well, we've seen it before and we know it's a good one. So over to you, Wolfgang.
Thank you, Georgia, for the kind introduction. As I said, it's just a selection of course slides we have made on this topic. And the selection I made is mainly focused on data acquisition and the monitoring proper. I hope the presentation will work. Let's see if the first slide appears. No, it doesn't. So, okay, now it's working. Can you see it? Hopefully. As we are going to use this little presentation as the starting point for a discussion, I think it's very good to learn your own experience on these matters. The fact that, of course, any monitoring will only be as good as the data it creates. And in this well, we face the general challenge that it is very easy to gather a rough set of data, and it's progressively becoming more difficult if you want to learn more details about what is going on in the building. For example, reading the utility meters is really straightforward, while determining distribution losses on or heat generation losses is requiring heat meters in special places. We will see an example very soon, which becomes a lot more costly for the installation, which will require then specialized design documents, and of course the logging of the data becomes an issue by itself. That is not to say that very sophisticated monitoring were necessary in all cases. Much can be learned from regular meter readings. For example, we did a monitoring in a large office building, 3,000 square meters, and the idea had been that the building automation system would log all data, which it didn't quite do as intended, while the people who were operating the building recorded monthly all important meters, and this was the basis for a very successful optimization process, actually, even though we only had this rather simple data set available. But if you want to know more, then it also depends, of course, on the equipment you have in your building. For example, if you have a solar thermal system and you have no heat meter fitted to the generation of this solar thermal system, then you're kind of lost when you want to set up energy balances at some time, because an important fraction of the heat that is being used in the building is just not measured. Heat meters for solar thermal systems are special. You normally cannot use the standard ones because they operate at higher temperatures than normal hot water systems, and they do not use plain water but a mixture with antifreeze, and so they need to be programmable for the thermal capacity of the fluid. But these are available, and if you want to know about a building with a solar thermal system, then it must be clear that you can only set up energy balances if you have this data available. Electricity is normally straightforward when it comes to a utility meter. On the other hand, similar things apply when you have a photovoltaic system, and you normally have a separate meter for the feed-in, but if you do not have a meter for the total generation, then you are getting lost a bit. So some inverters, they provide this functionality to log all the generated electricity, at least to some accuracy. But if you're not positively sure, then make sure that a sub-meter is fitted for your evaluation purposes. In some projects, it's also interesting to know about the water consumption, but that's an aside. Rather, normally in normal dwelling situations, it is not of great interest to log the cold water usage in detail. It's rather interesting if you have an apartment building to know about the hot water usage in the individual apartments, which might be metered in some form anyway for billing purposes. But even if not, then it's quite interesting because domestic hot water usage varies so greatly that it's really hard to guess what is going to happen in a particular apartment unless you measure it. This is one schematic from one of our monitoring projects where we really had heat meters for all kinds of different heat flows in order to determine not only how much domestic hot water has been used, but also determine the efficiency of the gas boiler in the first place. How much heat did this thing put out for the gas that was also metered, of course. How much heat was put into the cylinder and how much was taken from the cylinder and pumped into the circulation pipe. How much how much was lost in the circulation system, the solar input, all these things. And in this particular project, we went even as far as having heat meters for the hot water in all the apartments, which really was a crazy amount of data. And you can normally do that only for scientific purposes, I guess. But if you have a particularly advanced building services system that you figured would be an advantage, and you want to really learn whether or not it's worth the effort, then this is something you would want. Yeah, this is the subset in the apartments where we had heat metering for the heating circuit and another heat meter, which is not shown here, for the domestic hot water usage within the apartments. When it comes to heat pumps, we would like to see a heat meter and an electricity submeter fitted in all cases, because otherwise you can never determine whether or not this heat pump is operating in a reasonably efficient manner. And to calculate the proportion of heat you get out of this for the electricity consumed, you just need those two quantities. Hopefully someday it will just be a standard feature of heat pumps to measure the electricity consumed and the heat put out. But even then, you need to be aware what electricity is included, whether it is only the heat pump proper or the auxiliary pumps and controls as well, which can make quite a difference in the coefficient of performance you calculate. If you have a solid fuel boiler, then of course it's less easily metered what you put in as fuel. But in a school building we monitored, we just had a list or a log of the sacks of pellets consumed by date, and these 20 kilo or so sacks were a reasonably fine unit of measure for a 3,000 square meter school building. Well, for electricity, of course, you have a utility meter, and for a normal house, this will be plenty good information. But if you're interested in the electricity consumption and efficiency of the MVHR, then it might be a consideration to at least temporarily fit a simple plug-in submeter like this, if you have a decent grade one. Some of those are really not very accurate, particularly at low power, but if you have a reasonably good one, then it is fine. And there are also some where you can insert an SD card and have a log over time to see for changes or different ventilation unit settings, how much power is consumed. And this can inform you about whether or not the pressure drop in the system, for example, is at least roughly in line with what you have estimated in the design. With water consumption, we have mentioned already, it's normally of less significance, but in some projects it's interesting also to see the negative contribution to internal heat by cold water usage, and then it might be informative to have this data and to have it in a temporal resolution. So you see whether or not the cold water pipes have been stagnant for longer times and taken up more heat, or whatever has happened. Then there is a recipe for very, very simplified monitoring, which I would like to introduce very roughly, because it can be applied in almost any case where monthly meter readings are available. So if you have a house and monthly meter readings for gas consumption, if we assume a gas boiler as heat source, if there's a solar thermal system, we of course need monthly data on the generation of this. And we ask ourselves the question whether or not the space heating consumption was in line with what we have calculated with the PHPP. Then we can at least estimate something that is useful, even if it's not totally accurate, of course. So if we assume this was a house of 150 square meter and we have total metered energy in terms of gas of 50 kilowatt hours per meter square and year, then we can use figures from experience from many monitoring projects we have done. For example, for conversion and storage losses in the range of 12%. For the simplicity, we assume we have not the complication of the solar thermal system, but we can see from the heat consumption during the summer months, and this is why it is so important to have monthly data, we can estimate the domestic hot water fraction within the total, and then conclude that the remainder was the space heating consumption plus some distribution losses, which in this case amounts to just short of 20 kilowatt hours per square meter in year. So if this is all we have, then at least we have something, and we can see that we have calculated a passive house as maybe 15 and we come out at 20. So it's not exactly there, but it is not too bad either. However, if we know something about the indoor air temperature, which in our monitoring projects regularly turns out to be something of 21.5 degrees or even 22, so higher than the 20 degrees we have anticipated in the PHPP, then we can account for this, and we can either just have the simple approach and estimate 2 kilowatt hours per square meter and year per Kelvin elevated temperature and end up with 16.6 in this case, which sounds very much more like it. Or we update our total PHPP energy balance with this temperature and then come up with a somewhat better estimate for this particular building. And to this end, we do not need very much more than maybe logging the temperature inside and monthly meter readings, which can be taken manually. No need for electronic data acquisition, and still come up with a reasonable proof of general performance. So another aspect, so this is a cut. Another aspect of performance evaluation is, of course, the evaluation of continuously logged data. And I have picked an example of this from a school building. This is the temperature in one of the classrooms, which we might see on our screen just as shown here. And just ask the question, what does it mean? Is it good? Is it bad? What can we conclude from such data, or how can we make it accessible if we want to find out whether this newly commissioned building is performing as intended or not? So it's particularly for a school or other non-residential building, it's good to know about the weekends. In weekends, the building is generally not used, and no demands are put in for thermal comfort in those times. In schools also we have holidays. So if there are no internal gains and no usage of any kind, we do not have to bother about this decrease in temperatures. What more can we find? We can overlay or compare the timeline of weather data. So in this case, it's the blue curve is exterior temperature, and in orange we have the global horizontal radiation. So we can see the radiation spikes, of course, correlate with increases in exterior temperature, but also very much seen in the interior temperatures. However, normally we do not have a high-grade weather station on the building. And in this case, the school is located at 140 meters above sea level, but the nearest weather station is geographically very close, but at a considerably higher altitude. So we must consider this and not forget about the differences that are caused by this fact. On the other hand, if you have a school building, you have more than just one classroom and you want to gain an overview, it is very informative to just see the continuous timelines, but it's a bit laborious if you have to click through 20 such timelines and in every case interpret what you see. So it's a possibility, at least, to have the system programmed to make a statistical evaluation and represent data from many rooms, for example, in such a way that you show the extremes, the low and the high, and the 50% in between, and the median in this example in green. So you see that it has normally been around this temperature, and the majority of values are very close, and only short-term deviations have happened. And we can compare a whole month of data for 3 rooms very easily. So it's also about preparing and doing the number crunching in a way that is convenient for the evaluation. And we hope that in the future, building management systems will be better at incorporating such functionality. So another cut and view on what is happening with the PHPP. We're currently working on implementing this in the PHPP 10 to be able to update the energy balance you have done in the design process with measured data from the building and from the weather, in order to come up with more detailed estimates than the very simple monitoring we have been looking at before. So in this case, you see an example from the weather data sheet, where we can use the normally available weather data, which is exterior temperature, relative humidity, and global horizontal radiation, to produce something in the format of the PHPP climate dataset that can be used in the calculations to solve the energy balance calculation with the actual boundary conditions that have prevailed in a certain period of consideration, and not with a standardized climate dataset that reflects the average of 30 years or so. So we can do that with exterior boundary conditions. We can also do that with internal boundary conditions, temperature and relative humidity. There will be a little tool to come up with an area weighted mean of interior temperatures. It's a bit easier to combine readings from different rooms into an aggregated figure. And the result, ultimately, for space heating will be something as we see in the slide. So we have in red the nominal space heating demand as predicted with the boundary conditions we have fed into the PHPP. But we have an upper and a lower curve as well, which result from measuring uncertainties. So whatever we measure has an uncertainty. We are never positively sure about the exact value. And depending on the measuring equipment, this uncertainty is smaller or larger. And it combines in different directions. So we can have errors in the global horizontal radiation and estimate the radiation as higher than it really is. And if we at the same time read the internal temperatures as slightly lower than it really is, then those two combine with a prediction of particularly low space heating demand. So we come up with an error band with great hue here, and actually mathematically all results that are within this error band are equally probable or plausible. However, if we know that in a summer period the heating system was shut down, really physically shut down, then of course we have additional information that this is of course mathematically possible, but it's not physically possible. So some interpretation is still required. But I think it will be a great help to come up with a somewhat standardized approach to simple building performance monitoring. And of course, we can also give the final energy values, not only the pure useful space heating demand. If we have data on electricity as well, then we can, of course, come up with detailed figures like an updated PER sheet. So I think it will be helpful to also spot unclear points or malfunctions in buildings if we have a PHPP that is after commissioning updated month by month with all those metered figures and logged data, and then looking back, you can see for each month whether or not you are in this corridor or whether anything is out of control or suspicious. Yeah, in this case, it's summed up from month to month, and so you can more easily compare it with continually increasing meter reading. Yeah, that was it.